All right, so start things off to reward you for showing up on time. Also, I'm trying to incentivize attendance because I know if you fall behind in this class, it's going to be very bad, and I see some people already not really making sure they're keeping up with everything. So if you go to Canvas, right, I've got an in-class quiz up there. It's literally just, are you here today? I forget how I phrased it. Basically, that'll be the participation points. You'll get all of them today. I won't even ask you questions that you can get correct or not. This is a way for me to hopefully start to incentivize attendance a little bit. A lot of your econ majors, right? So if I tie some incentives to participate in class attendance, hopefully I should see the quantity increase, right? You want to supply yourself. So get on, get that done. I've got it set to close out in like 5 minutes. So pretty easy. Like I said, as you're doing that, just getting logged on, click on this in-class quiz, click yes, submit. I'll get those uploaded, kind of change the grade book to reflect the total participation points for the class after I get back to my office. Okay. Is that clear to everybody? Okay. So if you didn't hear me, did you hear me talk about the quiz? All right. So other than that, I've had quite a few people stop by my office. We've worked on everyone so far. I've been able to get their kind of state of working. So if you're still having issues with that problem set is due right on the 17th. So this is going to be what is that next Tuesday before we meet in class, I believe is what I have it set to be. So before class starts, I wouldn't suggest waiting until Tuesday to submit it. You'll have to get that problem set submitted up on Canvas. I've already mentioned you can just submit a do file, add comments in when you need to put kind of what the answer is, or if you want to kind of have your do file and write your answers up in a Word document, you can upload multiple files there. Like you can do it that way as well. Okay. Other than that, before we kind of jump in, finish up that module 2, whatever, chapter week 2 material, and then jump into regression. Any questions for me before we get going? Good. Okay. After class today, we'll also cover everything. You'll see the first quiz. Which, where's it at? You guys can see it yet. So I've got that first quiz kind of set to be available. I had it set to be noon. Doesn't make any sense. Hold on. Change this. I think I meant to select one. I probably just got it. There we go. So basically, after class, that quiz will be available, and that's due by the end of the day, Sunday. Right. So I want you to kind of focus on that. You can get that done by the end of the day, Sunday. You also have that kind of concurrent problem set. Those practice problems that are up there are very reflective of the types of questions you'll see on that quiz. These quizzes are meant to be not difficult, open book, open note. I give you those practice problems. It's really a way for you to trying to improve your learning as we progress throughout the semester. Okay. All right. Any other questions from me before we get going? Good. All right. So let's dive back into where we left off. We were talking about critical values, right? In this critical value approach, and we kind of had our steps, right? So we had this assumed true mean. We took a sample and we saw a sample mean that was inconsistent with that. But was it inconsistent enough that we can reject that assumed true value? Well, what does inconsistent enough mean? Well, we had to find these critical values where we said if our sample mean ends up being a test statistic, which reflects the number of standard deviations away from the assumed true mean we are, if it's anything past a certain amount, we're okay rejecting. Because if it's 4 standard deviations away from the assumed true mean, our assumed true mean probably isn't correct. Right? So we compared the critical value to the test statistic, made our rejection decision. We also have a p-value approach. So hopefully this sounds familiar from 370. And I think it's a lot easier. So here, when we were finding these critical values, remember we had this like set probability. We said if the probability of seeing the sample evidence we found falls below 0.1, 0.05, 0.01, those are kind of our thresholds, then we're okay rejecting. It's the same idea here. We're going to find something called a p-value. If it's less than those threshold alphas of 0.1, 0.05, 0.01, then we can reject these different levels. So remember 10, 5, 1% significance level, 90, 95, 99% confidence. Okay? So I'm just going to start out. You can probably chop out a lot of slides by me just kind of drawing this out for us here. All right, so let's say I had some looking at different sample means, I assume kind of that true mean is right here. Let's say I see a sample mean down here. What I'm going to do for the p-value approach, going to start out very similar to the critical value approach, where I turn my test statistic into, sorry, I turn my sample mean into a test statistic, right? Now, I'll just use the standard normal distribution just to kind of make it easy. We said generally we have pretty large sample sizes, anything over 100, we can use the standard normal to approximate anyways. So let's say I turn this into a test statistic and I find negative 1.72. So I go to my table, I looked it up. So just to be complete, we'll go to this Z table here. Where is it? All the way at the bottom. Negative 1.72. So looks like the probability of seeing something that many standard deviations away or further is 0.0427. Okay. So I can look up my test statistic. I think that's what it was. I'm off the third or fourth decimal, whatever the value was we just looked up. So I think it was 0.0427. So what this represents is, this is going to be our p-value. Now this would be if it's a left tail test, so just a one tail test. We'll talk about a two tailed in a second. And what it reflects to me is, it's the probability, my p-value is the probability I saw a sample mean that was as inconsistent with what I assumed to be true, or anything even more inconsistent, right? I use this terminology of even more inconsistent because when I'm dealing with negative values, that would mean anything to the left. If I found a positive test statistic, being more inconsistent would be anything to the right. Okay. So this represents my p-value. If that p-value is less than any of my alphas, then I can reject at that level. Well, here it's definitely less than 0.1, just less than 0.05. Not less than 0.01. So I can reject at the 10 and 5% significance level, but not at the 1%, right? It wasn't inconsistent enough with what I assumed to be true to be able to reject that assumed true value with 99% confidence. So this lines up with the critical value approach, because if I think about what the critical value approach I was doing is, I was saying, okay, look, I know there's this threshold, let's call it, do a threshold alpha of 0.05. There's going to be some corresponding critical value with getting that area of 0.05 in my tail. Well, now notice, I can compare, I think if I look this up, it's going to be 1.65 approximately. Notice anytime my test statistic is to the right, or sorry, to the right, anytime my test statistic is to the left of my critical value, it's in that rejection region, what is automatically going to happen, my p-value relative to alpha? It's going to be smaller. So my critical value approach will give me the same exact decision as my p-value approach. Okay. So there's like two sides of the same coin. Right? This is just different ways of doing this. Right? Now, what if this was a two-tailed test? So if this was a two-tailed test, what's my p-value going to be? Well, it's still the probability that I saw sample evidence that was as inconsistent with what I assumed to be true as what I found. But now, what would have been equally as damning evidence against that assumed true value? Seeing something not 1.72 standard deviations below, but anything over here would have also been equally as likely for me to find. Now, I only take one sample, so I'm only ever going to see one sample mean. But if it is a two-tailed test, and I'm just saying, I'm assuming it's exactly equal to this value, I could find evidence on either side that's inconsistent with that. When it was just a left-tailed test, evidence on the other side supported the null, right? So here I can find the area that's more extreme, the probability of finding my test statistic are more extreme, but I know that for every single value in that range, there was another equally damning value on the other side of the distribution. So this really only represents half of my p-value. How do I get my total p-value? Multiply that area by 2. Okay. So now here, if I was doing a two-tailed test, finding the same sample evidence, my p-value now becomes what? 0.0854, right? Now notice, is that less than 0.1? Yes. It's no longer less than 0.05. So with a one-tailed test, finding the same sample evidence, I might be able to reject the null. Two-tailed test, I'd actually be failing. Okay? So kind of hit on this a little bit later, but other things that are going to make it harder to reject, a two-tailed test is always going to make it a little harder to reject the null. Okay. Any questions on this before we keep moving here? Like I said, hopefully it's kind of looking like a little bit of review. So back to the slides here. So ultimately, once I do find that p-value, my rejection decision just becomes, is that p-value less than alpha? Okay. Let's see if I can get this to work. I feel like it occasionally works, but I want to try to move around a little bit today. So let's see. My p-value approach, I kind of already said all this. There we go. So here's my steps. You guys can see, there we go. It's a little sensitive sometimes. There we go. So here's my steps, right? It looks the same initially as my critical value approach. Figure out my null alternative. What are my levels of alpha? 3 benchmarks, those are always going to be the same, so that step's easy. Still have to calculate our test statistic. Now, if it comes from a student t distribution, it won't be a z test statistic, it'll be a t test statistic. Come from the student t distribution. Instead of comparing my test statistic to the critical value, what I'll now do is use that test statistic to find that p-value and then compare that p-value to alpha. Okay. So pretty similar, just a different way of kind of getting at this rejection decision. Okay. So at this point, I do want to show you some things that make it more or less likely, and this will really apply to linear regression stuff as well, but a lot of what we do this semester. So let's say I've got some assumed true mean for a test score, and I tell you the average exam score in this class is a 75. Right? I take a sample of you, maybe 30 of you, and I find, actually I think the number I'm going to use is 25. So I know the central limit theorem is not quite met, but it makes the math making points right here. So ride with me for a second. So you find a sample mean from these 25 students of 72. Okay. I then want to, so I had a sample size of 25, and let's say somehow I know that population variance was, what do I want here? Oh, so I want the standard deviation to be 15. Okay. So this is our setup. Well, what's the first thing I need to do, even if I'm using the p-value approach? I need to turn this value into a test statistic, right? I have a known population variance, so it's going to be coming from the standard normal distribution. If I only had a sample standard deviation or sample variance, we'd be looking at the student t. Okay. How do I do that? Well, I calculate this test statistic by taking the sample mean, subtracting the assumed true value of that statistic. So this is just sample mean minus assumed true mean. And then I'm going to be dividing by the standard deviation of the statistic I'm looking at. This is my other class. We're using y, I forgot. So the standard deviation of my sample mean, which we said we can write as the standard deviation over the square root of n. Now, another way we could have had that is the square root of the variance over n. It's mathematically the same thing. So I'm going to plug my values in here. This is what, 15, 25. So that's 5. So 15 over 5 is 3. Wait, is this what I wanted? It's not what I wanted. Sorry. Let's see, I found 7. Right? So 5 over 3 gives me 1.66 repeated. Okay. I could then look that value up in the table, right? And I could find that area to the left. I'm not going to waste time and go back to the z tables. It's going to be approximately like 0.4048 something, right? We actually can go through and look it up in the table. I just don't want to waste time going back and forth. So I've got this p-value, right? And let's say I'm just doing a one-tailed test for right now. All right, so just a left-tailed test. I've got my p-value. What levels can I reject at? Well, how do we make our rejection decision? We compare the p-value to alpha. So is it less than 0.1? Yes, so I can reject. Is it less than 0.05? Yes. Not less than 0.01, so I fail to reject. Okay. Everybody with me up to this point? Yeah.
I've understood so far the p-value compared to the alpha. When you go to reject, at least from the 5% or 10% level, you use the do you use the number of the score to test whether or not you rejected?
So we use our z score, our z value, to look up the p-value.
Okay.
So this 0.04 is our p-value.
Right.
So and I didn't write it complete, right? Is 0.04 less than 0.1? Yes. Less than 0.05? Yes. Not less than 0.01.
Okay.
Okay.
That makes sense. Thank you.
Any other questions before I make this more complicated? So what are some things that could change this, right? So let's do first thing. See if I can get this all on screen here. So what if I found, just this one's kind of intuitive, but we can kind of see it. ECON, writing without looking, ECON system, right? So if I found a sample mean that was even more inconsistent, so let's say instead of finding a sample mean of 70, I see 68. Well, what's that going to do to my numerator? I'm now going to have a larger deviation from that assumed true mean. So what's going to happen to my test statistic? If I find a sample mean that's further away from this assumed true mean, it's going to be a higher number of standard deviations away. So if I have a larger test statistic, I say larger in magnitude because we're dealing with negative values, what's happening to my p-value? Smaller. So is it more or less likely I reject the null? The p-value is getting smaller. It's more likely it's going to be less than alpha. So here, this would make it more likely I reject the null. Right? What about, and I think that's just intuitive. If I see a sample mean that's further away from 75, it's less and less likely that assumed true value is actually right? I should be more likely to reject it. What if I saw a larger sample size? What's that going to do to this fraction? Yeah, denominator is getting larger, so this is going to get smaller. Now, if my entire denominator for my z-score is getting smaller, what's happening to my test statistic, z-value? It's going up, right? Dividing by a smaller number makes it larger. So now, having a larger sample size is actually going to make it, well, if I have a larger test statistic, what's happening to my p-value? It's getting smaller. More likely I can reject the null as well. So this will be a recurring theme. Larger sample sizes are always generally a good thing, right? What if the original variation in the data was smaller? Well, what's happening to this fraction if this gets smaller? So this numerator is getting smaller, this fraction is getting smaller. My entire denominator for my test statistic is now smaller. What's happening to my test statistic? Larger. So the third thing is if the original variation in the data that we're sampling from is lower, it's more likely we can reject the null. Okay. And then we kind of already hit on this one, but what was something I also said that would make this same exact sample mean, we might actually fail to reject the null. If instead of a one-tailed test, this was a two-tailed. So we're thinking about a two-tailed test versus a one-tailed test. If I'm trying to list everything so it's more likely, the one that we're more likely to reject the null for would be that one-tailed test. And then everything else, we could have the exact opposite, right? These are all the things that make it more likely. What would make it less likely? A sample mean closer to the assumed true value. A smaller sample size. Larger variation or variance or standard deviation in the original data. Choosing a two-tailed test, right? So you can go in either direction there. Excuse me. Any questions on any one of those? Okay. All right. So I'll go through this kind of quick because I'm not going to ask you questions on the quiz or the exam about this, but I do want to introduce the idea because it might pop up kind of like I might use terminology of it throughout the semester. So when we're making this rejection decision, we can make errors, right? So it could be, for example, that I assume that this was true population value. I find a p-value less than 0.05, I reject. So I rejected the null. I then somehow get my hands on population data and figure out, ooh, true mean actually is 75. I was just unlucky and happened to get a sample mean that was kind of far away from me. So anytime we reject that null and it ends up being true, was I not switched over? This thing was, I'll point to that again. Anytime I have this p-value, right? Maybe I rejected that, but then I later find out that that 75 value was in fact true. So I rejected the null, even though I shouldn't have. That's what we're going to call our type 1 error, right? So whenever I reject the null, even though I shouldn't have been, right? And it's hard to see this. A lot of times it takes time to play out, right? It's hard. Sometimes we never get the population data. But if we did and we found out we rejected when we shouldn't have been, we're making a type 1 error. Anytime I fail to reject the null, so maybe I failed to reject there at the 99% level, then I get my hands on the population data and I see, oh, the actual average was 78 instead. So I should have been rejecting the null even though I failed to reject it. That would be a type 2 error. Okay? So you can kind of think about like a little matrix. Whenever I'm rejecting and then the null ends up being false, I made the correct decision. When I failed to reject and it ended up being true, I made the right decision, right? I should have been rejecting it. If I reject, even though the assumed true value was true, that's our type 1 error. And then when I fail to reject, and it ends up that I should have been, right, that null is false, that's our type 2. So I don't know, this always, I think, to me made sense. So if I assume that someone's not pregnant is my null hypothesis, I then kind of say, you're pregnant here, I rejected that null. Clearly, I shouldn't have been failing to reject the null, right? I'm rejecting the null when clearly I should have been. I'm making a type 1 error. Here, if I'm assuming that someone's not pregnant, and I say, yep, you're right, I'm not rejecting that. Well, clearly I should have been rejecting the null, even though I wasn't, right? So this is our kind of difference between our fault or our type 1, type 2 errors. I think if you're like in more in like medical terms, like they generally talk about it like false positives and false negatives. But this is our kind of terminology. So these type 1 errors, there we go, are going to essentially be our significance levels that we set. Because if I set that significance level and I say, I want to do this hypothesis test at that 5% significance level, even if this assumed true value ends up being true, when I saw sample means that were out here, I was going to be rejecting the null. How often, what was the probability I would have seen sample means out here? Well, probability, right? As soon as it falls below 0.05. So when I'm setting alpha, I'm essentially saying, even if what I'm assuming to be true ends up being true, I know that alpha would be the amount or the proportion of type 1 errors I'd be making. Right? So I'm okay with making a type 1 error 5% of the time. Right? Even if what I assume to be true is in fact true, I know that 5% of the time I'll get a random sample where I reject the null even though I shouldn't have been, but that's a pretty low probability. I'm okay with that. Okay. So that's what kind of type 1, type 2 errors. We'll use really that type 1 error because we're going to be using that alpha a lot. Right? We're going to be using that kind of cutoff alpha value. And I said similar to confidence intervals, we'll talk about those here in just a second. As I decrease alpha, I'm making fewer and fewer type 1 errors, right? And so this is why if I'm rejecting something with like the 1% significance level, that means that it's very hard to reject that, right? It's hard to get a test statistic out that far, but it's because maybe in certain situations, we really don't want to make a type 1 error. Like maybe like cancer screenings, we don't want to, if the null is that, I don't know. Maybe that one doesn't make sense because we need something where we're assuming that the person has, so we want to be, I don't want to be rejecting, for example, that you don't have a disease when in fact you do, right? If I'm, rejecting that, oh yeah, we assume that everybody has whatever this disease in our bloodstream, we rejected that you have it, so we're saying you don't. Well, if you actually end up having it, you're gonna die. So those type 1 errors, we really want to make sure we're not making a lot of them. So that's alpha, right? That's why we might want to choose a lower alpha value. And I won't waste too much time here because I'm not going to ask you questions on this. But type 2 errors, one thing that kind of comes out of it is having larger sample sizes actually reduces the amount of type 2 errors we're making. So we always like kind of larger sample sizes, once again, reoccurring theme. But I won't ask you questions about kind of type 1, type 2 errors. We'll use the terminology though later on in the semester. What I will ask you about and how to calculate are confidence intervals. Okay? So confidence intervals, we can think of if I had a range of values. So they're doing this a lot with election stuff right now. They're just doing it in a slightly different form. The easiest way to describe a confidence interval is within this range of values, I can say that there's a 95% chance the true mean is somewhere in this range, or 99% chance that it's somewhere in this range. Right? So just inherently, if I'm making larger confidence intervals, so going from 90, 95 to 99, what do you think is happening to the width of my confidence interval? As I say things with a higher level of confidence, my confidence interval needs to be. So if I tell you with 90% confidence, the true, average score in this class is between I don't know, 75 and 85. Right, the true mean is going to be somewhere in that range. If I want to tell you with 99% confidence it's within a certain range, what has to happen to the range of values I'm using? Yeah, it has to be a larger range, right? So how is that happening? When we have a confidence interval, what we're thinking about is whatever area we want outside of that interval. So 95% confidence, there will be 5% outside of it. We use that probability, the decimal form 0.05. There's 0.025 on each side of our confidence interval. Well, we know as long as we have that central limit theorem met, what's the z value that would give us 0.025 on either side? We can look that up. It's 1.96. So if I take 1.96 times the standard deviation of the statistic that we're looking at, that sample mean, and I go to the left and to the right, I know that there will be a 95% chance that the true mean is within that range of values. So another visual of this, right? If I were, there we go. So we've got this kind of range. If I could observe the true population mean, right? And I went 1.96 standard deviations to the left and to the right. If I then take a sample, if I were to see a sample mean here, automatically, if I turn this into a test statistic, what do I know this is fewer than how many standard deviations away? Well, this value, if I turn it into a test statistic, would be what? So I would take this value, I'd subtract the mean, so that would cancel. I divide by the standard deviation of my sample means, that would cancel. So I know that this value would become a z-score of, or a z-value of, negative 1.96. Every sample mean in this range is less than 1.96 standard deviations away. So if I see a sample mean anywhere in this range, if I were to go 1.96 standard deviations to the left and to the right, well, if it's only one standard deviation below, and then I add 1.96 to it, I'm always going to have a confidence interval for all of these sample means where my range includes that true population mean. If I had it on the other side, same kind of idea. This one is like, I don't know, 1.8 standard deviations away. So when I subtract 1.96 standard deviations, that's actually going to cross back over. This would be a confidence interval that includes a true population mean as well. The only confidence intervals that won't include the true population mean are going to be when I start to see sample means that are further than 1.96 standard deviations away. But I know no matter what the population mean is, the likelihood I see a sample mean out this far is only going to be 0.025 and 0.025. So for every sample mean in this range, I would have a confidence interval that doesn't quite include the population mean. And we could actually, I don't have a file for it. You could run a simulation like we kind of did for the NBA data, and take a bunch of different random. Maybe I'll do that for next class just to kind of show you. It's kind of fun. Maybe also good for me to brush up my skills. But run these simulations. I could go out and sample. Let's make it easy. If I sampled 100 different random samples, and then from those sample means, I built a 95% confidence interval around them. So I added 1.96 standard deviations and subtracted 1.96 standard deviations. I will end up with 95 of those, including the true population mean, and I would have 5 that don't. Or the proportion of, if I ran the simulation 1,000 times, it would be that 95% of those confidence intervals include the true population mean, 5% of them don't. Any questions on this before we keep moving here? Okay, so I think that's kind of a nice visual. So I'm going to draw this out for you so we can kind of connect these two. So say I have this true mean here. I go 1.96 standard deviations to the left, to the right. If I were to do a hypothesis test here, notice this is always going to be a z-value of negative 1.96. We can almost think about this represents the critical value that gives me half of alpha, right? Alpha total needs to be outside of this range, or it's like a two-tailed test, right? Half of alpha is on this side, half of alpha is on the other. If I were to look up 0.05 over 2, I'd find that 1.96 would be my critical value. So what will end up happening is, anytime I see a sample mean out here, I'm going to end up with a test statistic that is in my rejection region, right? So for any confidence interval, for any sample mean out here, I'm going to end up rejecting that null. But also notice, if I am more than 1.96 standard deviations, if I take that sample mean and build this confidence interval around it, didn't leave myself enough room, but notice it won't quite get back to that true population mean. So for every confidence interval that doesn't include the true population mean, I would also be rejecting that value. So we can use our confidence intervals to make rejection decisions as well, and it will line up perfectly with hypothesis testing. Anytime our confidence interval doesn't include a value, we essentially, those will also be a value that we could reject if we went through a hypothesis test. Okay. Any questions on this? Also, I feel like my regs aren't showing up as red. Let's see this. Does that make it show up any more contrast or not really? No? Okay. Right, here's my confidence interval. Doesn't quite include that population mean. Any questions on this before we keep going here? Also want to make a point because I think it's somewhat relevant and also kind of interesting. So in general, when you think about, a lot of times you'll see how do we do a confidence interval? It's going to be the z-value associated with having half of alpha on each tail. Here I'm writing it in more general form. I'm not choosing a specific alpha value. And then multiply that by that standard deviation. When I do these political polls, and you'll hear them say, it'll be like, the proportion of people say they're going to vote for Trump is 44%, with a margin of error of 2.3%. That 2.3%, that margin of error, is what you're adding and subtracting to your sample statistic to build the confidence interval. So, for instance, if we said, and it's just kind of a unique case, I think we went through an example last class where we said, if I have a 1-0 variable and I calculate the mean, it's another term that we often just refer to that as. So if I have a 1-0 variable, when I calculate the mean, it's going to add up the number of ones, divided by the total number of observations. We said we can think of that as a unique case where we're actually looking at a proportion. All right, it's still a sample mean, but a lot of times we'll use this terminology if it's a proportion of the data that belongs to this category or that would have that 1 in there for that variable. So they might say, the proportion of people who report they're going to vote for Trump from our sample was 44% or 0.44, the proportion of people that were going to vote for them. And then our margin of error maybe was 2.3%. So in decimal form, 0.023. So anytime you hear these reported things with like a margin of error, you could build this confidence interval. So it'd be what? 0.4177 to 0.4 6.3. All right. So here's my kind of confidence interval. I get some math in my head wrong. I don't need this 7, do I? Sorry. So I could build this confidence interval, and then I could look at you and say, if you told me, well, I think, I'm assuming that the proportion of people who are going to vote for Trump is 48%, 0.48. Well, based off the sample evidence I found, I can tell you that that's probably not the true value, right? With whatever the level of confidence was they built this margin of error with, I can tell you with that level of confidence, that's not likely the true population mean. Okay. Any questions? Another idea before I keep moving here. Okay. So I've got one more thing. Where are we at on time? Oh, perfect. So finish up here. We don't have to just do hypothesis testing for a single statistic. It doesn't just have to be for the sample mean. We can do it for a bunch of different statistics. So here, the statistic I'm interested in is not just one sample mean, but the difference in sample means. So here's the statistic I'm interested in, the difference in sample means. Well, just like with one sample mean, I then subtract the assumed true value. So the assumed true difference. Now, usually, especially when it comes to like the political polls and things like that, most examples, we just want to know, is there a difference? Is that difference anything other than 0? So we start out stacking the deck against ourselves. We assume there is no difference. If we can find from our sample evidence that there is a difference, maybe we can reject that. I then divide by, just like before, we divided by the standard deviation of our sample means. Well, now we're going to be dividing by the standard deviation of the statistic we're looking at, which is the difference in sample means. I wouldn't expect you to know this but all you have to do there, whenever you're looking at the difference in two variables, the variance of that difference is adding up the variance of each one. So from each one of these sample means, we would have the sample variance over the sample size, add them up together, that would give us our total variance for that difference variable. So I'm just going to throw this at you. You're never going to have to kind of plug these in, work this out by hand, but I'm going to show you how we can get Stata to do it pretty quickly. Okay. But it's the same idea. Once I have my test statistic here, I'm using sample data, so we would have to use the student t. I can look up the p-value, I then compare the p-value to alpha, and all the same rules apply. If my p-value is less than alpha, I can reject. If it's not, I fail to reject. Right? Now we can do this also, and we won't dive into how we do the hypothesis testing for these, but you can do any statistic. Covariance, correlation, coefficients, we can do hypothesis testing for any statistic that we want. And it's always the same format. Take the sample statistic, subtract the assumed true population value, divide by the standard deviation of your sample statistic. So we'll see this in regression, probably not today, but next class for sure. Okay. So at this point, I do want to finish up. Oh, I thought I had it pulled open. Just accidentally closed it. We'll pull up Stata, right? So go to IU anywhere. Yeah. Scroll down here. Open this up. Open up the launcher. So we'll use that review of statistics do file from last week. And then I'll also open up the linear regression one just so we have that for later on, because we will get to take a look at that here today before we're done. There we go. So I'm gonna go to File, Open. I'll open the regression one first since I'm already in this folder. I'm then gonna go to File, Open, and I want Review of Statistics. So this is what we were looking at last week. I'm going to scroll down here. I think this is the one that I want. Yeah, so week 2 code, right? So we're going to be down here on line 42. I'm going to set my global. Right? Now, for a lot of you, just to get this, I think I'm getting some questions on it. So just to show you, your global will be as simple as if you're just dropping them into your OneDrive, that's going to be your path, right? If you do create a folder, might be that, but you should have a very short kind of path you can put in here, and then you can run all the code that I gave you because it'll be using your specific OneDrive. So I've got mine set. I'm then going to go to import this election data. Oh, is it in the wrong folder? Did I move it? I got something wrong. So if I ever am having issues with the path, I don't want to waste time. I will go to, oh, I bet it's in the week 1 materials, that's why. No, it's not. Where is it at? Oh. There's an Excel file. So we'll go to import an Excel file. There it is. It's in that week 2 folder I had. I'll open it up. I'm importing the first row as variable names. I'm using the non-missing tab or the non-missing kind of worksheet there. I'm gonna hit OK. So what did I have wrong? I had something wrong in my do file. Oh, I deleted it already. There we go. I might have been using the wrong section. So anyways, here we've got it imported, right? We now want to start to do some things. So I think we did a lot of this last class where we renamed some variables. I had this in there to show you, like, once you rename it, it no longer can recognize. So if I try to run that, code twice, that old variable name is no longer in there. So I can't do that. So I'm going to then go. So you want to, you can't do it twice. That was just something I wanted to show you last class. We could look at the distribution of unemployment. We ended up saying I can create variables where I'm looking at, I want this new variable that is the mean unemployment across all the counties in this data set. So we use the ECON, where it had this built-in mean function to create that variable, which gave us, whoops, not too far, the mean unemployment, right, of our data set. The next thing that I had in there, like I said, I believe we did this in the last class, is I created this new 1, 0 variable, right, which was a 1. So generate this new variable high unemployment, which is a 1 if this statement in parentheses is true. If that county's unemployment was above this employment mean we just calculated, put in a 1. So basically this variable is going to identify all the counties that had above average unemployment, and it's a 0 if they had below average. So we'll run this. Sure enough, if we looked at the data, we now see every county with unemployment below the average is a 0. This one just barely above the average gets a 1. Okay. So once I have these kind of categorical variables created, we can look at them. We don't need to do this for today. I'm going to create some additional variables. So we're just going to go here. We talked about all this last class. This was our conditional means. So this is where we left off, but I just want to kind of revisit the example. So I'm just going to run all that code. It's thinking. It's being slow. So some of the other variables we created was this high income, just a 1 if they had above an average income of 75,000. This is like extremely high income counties. I kind of had high proportion white counties, thinking about there might be differences in their voting habits, right? So the question I might have is, okay, is there a difference in the proportion of these counties that vote for Trump in low unemployment rate counties versus non-low unemployment rate counties? So what I can do is use this built-in t-test function, and it's essentially going to do a hypothesis test for me for that difference in between those two groups' means. So what this will do behind the scenes is say, okay, look, take this variable, use this other variable, it's a 1, 0 variable. So this should always be like a 1, 0 variable that you're using in this part. It says take all of the 1s, take all of the low unemployment rate counties, calculate the sample mean proportion of them that voted for Trump in the last election. Then take the other category, the 0s, so these will all be the high unemployment rate counties, calculate the sample mean proportion of those counties that voted for Trump, calculate the sample variances, calculate the sample sizes, throw them all in here using the assumed true difference of 0, calculate a test statistic, look it up from the student t-distribution, tell me the p-value. So Stata is going to do all of this work for us behind the scenes. Okay, so we go back and I run this t-test. I also have to add in this unequal. So there's an option where you can tell it if the two groups have equal or unequal variances. More often than not, we're going to have two groups that have unequal variances. We don't want to assume that they have the exact same variance. We might want to assume they have the same variance if we know that something about like usually it's like more of like a biology thing where we know the underlying variance of these two groups is exactly the same. So we want to make sure we know our sample variances will be a little different, but we know it's coming from like the same kind of distribution. Almost all the examples we'll look at, we have no idea about what the variances are, so we'll just assume they're unequal. So I had to add that kind of line in there, but once I run this code, and then go to look at the output that Stata gives me, oh man, it took both of these groups, calculated the sample mean, sample sizes, standard deviations or variances, right? If we have one, we automatically have the other. It then created this like difference between the means, calculated our test statistic. Our test statistic was -7.9, right? It then did the kind of looked up the p-value for us. We'll notice here for a two-tailed test. So in order for this one probably makes sense. I'm assuming that there's no difference in the proportion of these counties that vote for Trump in low versus high unemployment. Probably, we know that's probably not true. Sure enough, I'm 8 standard deviations below that, and my p-value is basically 0, right? So I found strong evidence here that actually low unemployment rate counties actually tended to vote. How did it set this up? My one was low unemployment. So it set this up as 0, was my first one. So high versus low unemployment, the high unemployment rate counties actually tended to vote less for Trump, right? Low unemployment rate counties tended to vote high. But at the end of the day, all I'm looking for is there a difference, right? And that p-value of 0, I can say with 99.99% confidence that there is a difference, right? I can reject this assumed true difference of 0. And notice it doesn't give me the null here. For whatever reason, Stata tells me the alternative hypothesis, which is if we assume it's equal to 0, the alternative that's not equal to. We found pretty strong evidence that supports that alternative hypothesis. Okay. Any questions over anything there? So this might be a point also that I'm getting some questions about like the exam, obviously a little bit further out. I'm not going to make you use Stata on the exam, like you won't have your laptop pulled up. It's going to be paper, pencil, and a calculator. But I might on the exam embed output like this and say, you know, and maybe the p-value is a little more interesting than 0. Maybe it's like 0.02. And I say, what levels of significance can you reject the null hypothesis that the difference is equal to 0 at? So it will end up on the exam, but I'm not going to make you tell me anything about specific code. All you need to know is how to interpret the output that we're getting from Stata. Okay. Is that clear? You guys are quiet. I get worried that I'm like not saying something clear, and I like the head nods. The head nods help. So I'm gonna go back here. We can do it for other ones. I just thought it was kind of interesting. I played around with this data for a while. Forget where it's from. You could probably just Google search like 2020 election free data, and just it's out there in the ether of the internet. But I did this for high income counties. I noticed kind of that difference, a very strong kind of difference there, a test statistic of 10. Once again, we can definitely reject that there is no, saying that there's no difference between portion of counties voting for Trump in the high versus low unemployment rate counties or high versus low income counties. We can strongly reject that, right? And then high proportion white, we also kind of -20, right, is even more of an extreme difference from that assumed true value of 0. Okay. All right. Any questions over that? There's one more thing I want to show you in Excel before we can go back and jump into week 3 material. Okay. Good. So I don't know if I mentioned this command, and it just can be useful. So let's say, really there's 2, and you won't want to use the one a lot, but I'll show it to you. Let's say I'm just going to create a variable, and I don't know, I took Trump 2020, and I want to divide it by 100, maybe it was in percentage form, and I wanted to get it into decimal form. Well, I accidentally hit 10, I ran my code, and I didn't realize it. Okay, I don't want to just keep creating new variables, like, and leave the old ones in there. So what I can do is use this drop command and say, okay, I want to drop what variable, the one that I just created because I created it incorrectly. So it'll drop that variable. And now I can go back and correctly run it. Right? Now, if I want to save my work, once I get that correct code, I either want to delete this line of code or I just want to make sure it doesn't get ran again, right? But that drop command can be helpful to like get rid of a mistake that you made. It's also helpful if I just have like a big data set. So if I'm looking at something like this, I've got a ton of variables and I'm not using like any of these in the middle. So if I select these, oh, actually, I want to do it that way. I want to go over here. So let's say, yeah, we'll start here. Let's say I don't want all of these variables. I'm not using them. So I selected them all. I'm going to copy this variable list. So this is just right clicking. You can actually copy the variable names so you don't have to type them all out. Paste them over here. They're just kind of mudding up my data set. I'm having to scroll through them a lot, so it's kind of a pain. So what I'm going to do is I'm just going to drop all these. Now, it's not quite as wide. Now, this isn't a great practice because once you drop it, it's gone, right? So you have to really make sure you don't want those variables or you're not going to need them moving forward. But that is something you can do to kind of be helpful just if you're messing around with this on your own. Because, you know, if you find anything you're interested in, you can always, I mean, there's so much, like I said, if you're interested in anything, you can Google whatever it is, free data, Excel, free data, CSV. There's probably data files out there. You can import them into Stata and kind of start playing with them. Like I was doing this thing for, I'm still kind of working on it, but there's like free betting data out there. So, on like sports betting, you can try to figure out what pitfalls people are making based off of the bets that are getting put in. And we can use things like linear regression to estimate where people are making errors and where you potentially could capitalize on. Now, that's just a hypothetical. Anything you're interested in, you could use something, right? So that takes care of that. The next thing we're going to talk about, and I hate the beginning of this class, and I'm probably not supposed to say that, but I don't like doing all this review stuff, but I know that anyway, we need to kind of get us all up to speed. So now we're going to dive into what I think is a little bit more fun, but we got to understand the basics before we really see its power. So linear regression, which you probably talked about in 370, but I'm going to sprinkle in some stuff that they probably didn't talk about even in the introduction of it. Okay? So in general, what are we trying to do is we have two variables and we know, okay, as one increases, is the other tending to also go up? Is it going down or is it not changing at all? What's the causal relationship between these two variables? So in general, you've probably seen this from other math classes. I don't know why I wrote it like this, because I know that the way that the people in the math department say it is like this, right? So y equals mx plus b is probably something you've seen at some math class, right? That's all we're doing in linear regression, right? We're just going to kind of use slightly different notation, and there's a reason why, because we're eventually going to make it a little more complicated, but we've got this y variable, which we think is a function of x. Now, for now, we're keeping it a linear function, right? So there's going to be some intercept. We'll call that beta 0, call that our intercept coefficient. And there's going to be some slope coefficient. We'll call that beta 1. Okay? So we're going to try to figure out what is this relationship between x and y, modeled right now just through a linear relationship. Okay? And we're going to use our data to do that. So some terms that I'll use, that y variable is what we call our dependent variable. It depends on x, right? It's a function of x. X is going to be our independent variable. Now, we'll eventually, maybe even next class, start talking about we can have multiple independent variables on the right-hand side of our regression equation. But for now, we just have one. So it's the thing that is changing. As x changes, it causes y to change. Okay? So if I'm thinking about kind of our ordinary linear regression, we usually call that OLS. Right? We look at the data. Let's say I had this data set, some x and y value. I then plot every single observation. Okay? If I were going to try to draw a line that best fit this data, I would say kind of something like this. Right? Now, that line is essentially going to be this equation. Right? We're going to have some intercept, and then we could calculate the slope, right? Slope's not hard, change in y over change in x. That's all we're doing there. Okay? So this linear equation captures the closest we can get to describing from the data this relationship between X and Y.
Is that supposed to be B0x or B1x? In
B-
formula.
Here? Oh,
Yeah.
thank you. I probably copy pasted, I didn't get the subscript changed. There we go. Thank you for saying that. So yeah, so we've got this equation, and it's going to tell us this line that best fits the data. Right? Now, we can have all kinds of relationships, so no relationship, positive and linear, negative and linear. We won't jump in there quite yet, but eventually we're going to get to actually figuring out relationships that aren't linear. So we don't need to keep that equation linear. We can actually add quadratics, things, cubes, whatever we want. And it can be convex, concave. We can estimate either one. For now, we got to walk before we can run. I'll keep everything linear. Right? We'll just assume we've got linear relationships. So I'm going to draw this out, and then we'll just look at the summary. I think I've got the slides. But it's just another way of thinking about this. So here's my X and Y. I'll draw an upward sloping one just to make a little more sense here. So here's my data. I draw a line of best fit. What this line is essentially, if I plug in different, and here, I'm going to add some more dots out here. If I plug in different values for X, I'm going to have some values for my slope and intercept that come up with, okay, at this X value, just to put a number to it, call it 5, here is my predicted Y value, right? So our regression equation, once we get values for this intercept and slope, we'll have, basically that's our line of best fit, and it's telling me for different X values, here's the predicted value for Y. Now, the actual value for Y, for any one observation, maybe this observation has a 5, well here. Notice it is 5, but the actual Y value is much higher, right? So for this one observation, the difference between the actual Y value and the predicted Y value is relatively large. So what we end up calling this is our error term, or epsilon. Epsilon is literally just the actual Y minus the predicted Y. So you kind of notice here, we're under predicting. These are going to be positive errors, right? Seems kind of weird because we're actually predicting it's too low, but that gives us a positive error term. The way we define the error is the difference between the actual and the predicted Y. Now notice for some observations, for X values out here, here's my predicted Y value, but for this one observation, the actual Y is actually below the predicted value. So our line of best fit is going to have some positive, some negative errors. Okay. What we're going to end up doing in linear regression is the whole reason this is a line of best fit. Think about what if I had this was my line of best fit? I'm making my predictions here. What's true about all my predictions? What's true about my error? I'm way off for every single observation, right? This line is way far away from the data. So the whole reason why we're kind of like, initially we think about just like you're eyeballing where that line of best fit is. We'll talk about mathematically, how do we come up with it? But you're trying to make it so that your predictions aren't very far from what the actual Y values are, okay? So with this idea in mind, right, we've got this error term. The book sometimes will call this U. I don't know why, because like everywhere you look in like any academic journal, you'll always see people use epsilon. So I don't understand why they use U. We also use U for some other things that some other error terms we talk about in this class. So ignore the book's kind of error if you even looked at the book. But epsilon is going to be how we write the error term in this class. So how are we going to find kind of what that slope coefficient and the intercept coefficient are, beta 1 and beta 0, got them right on this slide. How do we find the line that minimizes all of these errors that we're making? So said in a slightly different way, because I already kind of drew this out for you. How do I minimize the sum of all of the errors that my line is making? And not only the sum of my errors, just like the variance, we want to over penalize really bad errors. So this is the idea of when we square it, 1 squared is still 1, 2 squared is 4, 3 squared is 9. The larger the error, when we square it, it becomes even larger, right? So we're going to minimize the sum of the squared errors. Right? So for every single observation, we would make a prediction, look at the actual y, take that error, square it, do that for every observation, and add them all up. It's going to be a lot of work. State is going to save us a lot of time. We'll look at here in a second. Right? So I then can say, okay, how can I rewrite the error term? Well, it's just my actual y minus the predicted y. Well, the predicted y just comes from my linear regression equation. Right? Once I get to this point, I've got 2 unknowns. There's actual values in the data for x and y. So I've got like 2 unknowns. I can take a derivative of this function in respect to both of those. 2 equations, set them equal to 0. 2 equations, 2 unknowns. I can then do a bunch of math and find a solution. We're not going to do that math. People have already done it, and state is going to do it for us behind the scenes. Pretty easy, right? But this is the idea. We're minimizing the sum of the squared error terms. Oh, one of my animations is off. So we'll go skip ahead a little bit. But this is if you do all the math yourself. If you do take the derivative, set them equal to 0. Do some algebra. The slope coefficient that will give you that line of best fit that minimizes the sum of the squared errors is going to be this. Right? So it's going to be every observation's deviation from x times the deviation from y, add them all up, divided by the sum of the deviations from x squared. Well, what does this look really similar to? If I just divide both of these by n, what is that numerator? That's just my covariance. If I divide this by n, what would my denominator be? The variance of x. So from a simple linear OLS regression, my slope coefficient is actually just going to be my covariance divided by the variance of the x variable. And I'll prove this to you here in a second from stating. I know that's what it's odd, but that's the way the math works. Now the intercept coefficient, much easier. Once you have that slope coefficient, it's just the average y minus whatever that slope coefficient is times the average x. Okay? And like I said, you're not going to be plugging a lot of these values in. You're going to be getting a lot of this from Stata, and we're going to be using it that way. Okay. I already kind of jumped the gun here, right? Numerator, covariance, denominator is my variance. So, how do we do this in Stata? Okay. So let's hop over. Oh, I didn't need to do that. Is it still okay? Good. So now I'm going to open this regression in class file. Here, hoping I have, oh, this is not the right global. So what was the global I used before? We're going to go to open. I think I'm in week 3. I believe I want this birth data, right? So, okay, don't save, I don't really care. Let me just take my file path. You don't have to do it this way, but I want to have it for next class. And let's make sure we get it set correctly. I think I was using it on my computer last and I accidentally saved over the file. Oh, there we go. Oh, gosh. Okay, so now I'm going to set my global, open the data back up. Hopefully it's working now. Yep, okay, got the right path. So there's a way you can kind of get this from the drop-down menu. So you can go to like graphics, two-way graph. I think I created a scatter plot for you either last week or even Thursday, the first week. But the code is always the same. You just two-way in parentheses, you want a scatter plot, and what 2 variables do you want to scatter plot of? So I'm just going to run this so we can kind of get an idea about what this data looks like. Okay, it's it's pretty clumped together here. But I had this interesting question. I'm not the only one that had it. I read something about it and then I found a data set. But like apparently you heard of like these shale oil wells and they like get a lot of runoff. I guess that whatever the production process is, a lot of it ends up in the water. I think there's a lot of them in Pittsburgh and apparently it's like really bad for you to have oil in your water. So I had this idea of like, well, the number of shale wells that it have in these counties, they would maybe see higher levels of like stillbirth and like number of births might actually be going down just from a result of the fact that mothers drinking this water don't know, right? So it's kind of hard to tell from that scatter plot. So the scatter plots aren't always clear, but we can run a linear regression. And what it will do is it'll take those equations, right? It'll essentially come up with them behind the scenes, minimizing the sum of the squared errors across every observation in the data set, calculate that slope and intercept coefficient, spit them back out at you. So I just have to use my REG. I think technically the full command you can write is regress, but why type more if you don't have to? So REG is just regression. I'm going to choose my dependent variable to be the number of births, and my independent variable is the total number of shale wells in that county. I'm going to run this regression, and I get all this output. Now, we're going to use a lot of this. Some of it we're not talking about yet. But what we really wanted after today's discussion is I want that slope coefficient associated with my x variable, and then it calls the intercept a constant. Right? Those two terms are really synonymous or interchangeable. So I now have what my intercept would be, and I have that slope coefficient. Okay? I've got my two betas. Okay? I also very quickly, it tells me my sample size up there, so I had 170 observations. And notice, we'll talk about this in this class, but I'm starting to get some like p-values over here, some confidence intervals. So we'll start to be able to use those later on as well. Okay? But for now, I'm just thinking about how can I run this regression to get that intercept and slope coefficient.
I think I'm wrong, but is there a regression similar to testing the variance between the two variables?
Like a correlation or a covariance?
Yeah.
It's very similar to a correlation, not quite the same. So we want to be careful. And also once we start adding in more variables, it gets even further from being just a correlation. But if it helps, it's very similar to that.
Okay.
So, and to that point, just looking at time, I want to make sure we have time for this. I'll come back to this in a second, but I'm going to gloss over this just to make sure we have time for this, and it kind of goes to your question. So I said earlier, we can get this regression output from Excel, but what's another way I said we could find that slope coefficient? It was the covariance divided by the variance of our x variable. So I've got this correlate command here, I skipped this one. I've got the sum command here, we've already talked about, of these shale wells, comma detail. This is my x variable. So I'm going to run this, and I see that my variance is 77.48. So I've got the variance of my x variable here. I'm then going to use this correlate command, and then I'm going to put comma covariance. So this tells it to find the correlation, but report to me what that covariance is. So I'm going to run that line of code, and I get, okay, the correlation of total shale wells with the number of births is about -303. So I now have my covariance and my variance of the x, or the independent variable. If I divide -303.8 by 77.48, and you can put this in your calculator to prove it to yourself, but it ends up being -3.92, which when we ran that regression, what was our slope coefficient? -3.92, right? So a lot of these things that I say, you always prove it to yourself with data, right? The math, if we understand the math, we can rely on that, but it's always helpful to kind of see it play out in the data as well. Any other questions? Anything I just did there? And I just wanted to make a point here. We can run regressions, and often don't want to do this, but like later on in the semester, there might be some reasons why. And this one, it's kind of a good example. So when I'm running all this data together, there's a lot. If we look at that scatter plot, there's a lot of zeros, right? And maybe having more like shale wells in your county is like even worse for births, but all those zeros are like, we're finding really like no impact there. It's like greatly influencing our line of best fit. So maybe I just want to run this regression, and I'm going to add in this conditional statement, which is only if that total shale wells is something other than 0. So now I'm only looking at the counties that at least have one shale well, right? And then, okay, as I have more, what's the impact on the total number of births? So I'm going to run this here. Okay, actually looks like that coefficient's a little bit lower, so it's looking like it has a smaller impact, right? So maybe it's not that having more wells is going to be like super detrimental, but maybe it's just that first well, right? And so we can start to kind of run different regressions for like different subsets of the data. More often than not, we want to use all the data that we have, but we can kind of use these conditional statements, just like we did when we were creating means to find group means. We can run regressions for different subsets of our data set. Okay. Any questions over anything here? Okay, I want to get us set up for next class. So I've got a little bit more, but then I swear I'll try to go through it somewhat quickly. All right. So we've got these numbers. What do they mean? Right? So in general, if you had a linear equation, what is your slope telling you? It's telling you that every time x goes up by 1, you're adding that slope one more time to get your value of y. So every time x goes up by 1, the slope is how much y increases or decreases. So for us, we're going to have units, actual variables. So the general interpretation of the slope coefficient is for every additional unit increase in x, we expect the predicted y value to increase or decrease by beta 1. Right? I think I put increase up here, but technically, right, it can be negative. In our shale well, it was negative 3.9. How would we interpret that? For every additional shale well in the county, 1 unit increase, we would predict that the number of births would fall by 3.9, right, or close to 4. And I think those births was like per 100,000. I forget what the actual variable was, but whatever the unit of that y variable is, I think I might have just been number of births just to make it easy. Right? Now the intercept has kind of a weird interpretation, which is it's going to be the expected value for y when x is equal to 0. And this can sometimes be a little goofy. So I'll show you an example and I'll come up with one where the intercept doesn't make as much sense. So if I've got this data set I had laying around, I had self-reported marijuana usage and income, right? So I was like, oh, it's kind of interesting, run this. The income's low, it's an old data set, people like in their teens. So I ran this regression. And I only used 1 year of the data, so I kind of use this conditional, and I find these values, right? So how do I interpret them? Well, remember, the slope coefficient is for every 1 unit increase in x, so for every additional day, and I think it was each month that someone uses marijuana, they would expect their predicted income goes down by $253, right? If they use marijuana 0 days a month, how do we interpret the interceptor constant? If they use marijuana 0 days a month, the x variable is equal to 0, their predicted income would start out at about $32,450. So that's how we're interpreting these coefficients from this data output. Now, obviously, I'm not controlling for a lot of other factors here. So this might not be a causal relationship. We're going to move to including things so we can get closer to that causal relationship. But for now, this is pretty weak evidence, right? So evidence of a correlation, but probably not causal. Okay. Any questions on this idea? I'll show you one thing that can pop up that can be confusing to people, and then I'll let you out of here. So let's say I wanted to run a regression, and I had years of education, and I was trying to use that to predict somebody's income. So even if I take years of education, not college, but like just in general, so kindergarten counts as 1, first grade counts as 2. I could estimate that. I'm probably going to see, maybe the data looks something like this, and I get a line of best fit that looks like that, all right? So I'm coming up with predicted y values. Well, my intercept here is going to be negative. So how would I interpret that? Somebody with 0 years of education, their predicted income would actually be negative. How can you have a negative income? Well, this can happen when you have data that like starts further out. So for instance, if I had a data set with the years of education, how many people actually have 0, 1, or 2 years? Who is a first grade dropout? I'm sure there's someone out there that exists, right? But probably not. I mean, there's probably not going to be people like that in my data set. These predictions don't even make any sense because people they don't exist in the real world. So your intercept, you would still interpret the same way. It's still the predicted y value when x is equal to 0. It's just that in the context of certain variables, it's gonna seem goofy, right? It's gonna be, we can't have negative income. Well, it's still how we interpret it, right? And what that really does tell you is that the only way that that can happen is if you do have kind of like censoring of the data, right? It doesn't start until kind of further out. We don't have any of these low x values in the data set. Okay. All right. So, any questions for me before we get out of here today? So you'll see that quiz pop up. You got that problem set you can start working on. I'll be in my office hours tomorrow. Be a good time to stop by if you're having any issues with that problem set or any questions over the practice problems. For those of you who got here a little late, I used an online quiz. So if you weren't here when I mentioned that, come up and talk to me at the end of the class. I wasn't trying to penalize you for being a minute or two late. I was trying to incentivize more people to make sure they're getting to class. So come talk to me after class. All right. I'll see you guys on Thursday.
Downloaded the cell phone.